very good evening to all. Welcome to another captivating session of ASIA Sensemaker. In ASIA Sensemaker, we have informal conversations, yet they maintain a level of depth and expertise comparable to a seminar setting. Today, we have with us Professor Steve Easterbrook. He is the director of the School of Environment, University of Toronto, Professor, Department of Computer Science, University of Toronto. Professor Easterbrook is also the member of Sustainability Informatics Research Group, member of the graduate faculty of the School of the Environment, member of the Center for Global Change Science. His research work focuses on climate informatics and more specifically, the applications of computer science and software engineering to the challenges posed by the global climate change. He is also investigating the role of computational models and system thinking in teaching key concepts in climate change, climate science, and the application of web-based collective intelligence tools to the development of solutions to climate change. Today, we have a discussion around his book, Computing the Climate, How We Know What We Know About Climate Change. This book tells the story of climate models tracing their history from 19th century calculations on the effects of greenhouse gases to modern Earth system models that integrate the atmosphere, the oceans, and the land using the full resources of today's most powerful technologies. We welcome you, sir. Now, I would request the moderator for today, Professor Amog Rai, Research Director at Advanced Study Institute of Asia, to kindly open the session.
Thank you, Nidhi. Thanks so much for that introduction. Thank you, everybody, for joining it. It's 5:30 p.m. And we are still celebrating a festival called Diwali, Professor Steve. So, the after effects of that. And yet we have some people here who are interested in listening to you speak about climate. So first and foremost, thank you for coming and doing it. Thank you, everybody, for joining in. And now that we are about to formally begin our proceedings, sort of an hour plus 30-minute long conversation, hopefully, if you have the time. So this is going to be recorded. And what we do is that we record all of them. And we have a small seminar, 10 to 11 people who listen to these conversations. And when it goes online, it goes to a lot more people because we produce and edit it in a way that it makes sense for people to kind of jump into different paths. So, but before we do that, we're going to send it back to you for any approvals, deletions, so on and so forth. Having made these formal announcements, now with your permission, I would like to jump into the book.
Absolutely. Yes. I'm delighted to be here with you.
Right. Thank you. So first and foremost, for everybody who has joined us, this is the book. This is a very interesting book. It looks deceptively small, but it carries a lot of information in it. And it kind of tries and starts in the late 19th century and stops somewhere with the Nobel Prize in the physics that was awarded 2 years ago to 3 people. One of them, and you write a blog post on your website about it. So let me begin with that. How long did it take you to write this book? Because the blog post was 2 years ago, and it said, yes, an excerpt from my forthcoming book.
Yes, in fact, a lot longer than that. I've been working on this book for more than 7 years. And in fact, a lot of the work in the book goes back to studies that I did in 2008 and 2010, when I first started visiting climate research labs, kind of meeting climate scientists, looking at the way that they build their models, the way that they test their models, kind of understanding what these models are and what they do with them. And I struggled for a long time to think about what I would do with what I'd learned meeting all of these climate modelers, because it was all so interesting. And, as a professor, the obvious thought is, okay, I'll write some conference or journal papers about it. after a while, I realized that there's no book that that kind of captures, especially not for a general audience, what these models are and what they do. And I thought this would be really neat to try and put it all together in a book. It took me a few years to kind of get it straight how I would structure such a book, how I'd put it together. And then I wrote the proposal for this in about 2015. So that's 8 years ago. Sent it off to the publisher. They were really interested. And it's taken me that long, I think, to do a couple of things. One is to find the right voice. Because what I really wanted to make this accessible, I wanted to make it readable for people that don't know the climate science. But I didn't want to hold back on detail. For people that are curious, I want to give them the full picture. So kind of finding that right balance between, making it accessible, describing it in a way that would make it interesting, but for those that want it, telling them the whole story. That was tricky. Took me a while.
Yeah. And I can tell you this, that you have succeeded, because this does not have a lot of jargon, but it has the technical, you need to know some amount of technical words if you're going to get at the deep end of climate science. But I'm not a climate scientist. I'm an economist, and I understood parts of it. However, I've had some training in theoretical biology at a point of time. So some of it made sense. But I'm going to, before I started, because these conversations that we have, and the name of the institution is Advanced Study Institute of Asia. And so most of the times when we have a person on the other end, it's a political scientist, an economist, a geostrategist, you are an outlier, right? Because you are a computer scientist. From what I've been able to get from the book is that you're a computer scientist who worked at NASA, then decided to get back to teaching how to write a good computer software program. And from there, you make your way to the world of the anarchic way of climate science. Let's put it like that. Am I getting that detail correct?
Yeah, I think so. And I talk about that journey in the book as well. I wanted to give readers a sense of where I'm coming from, and my journey kind of through this world. Because I started out, I might be an outsider for your group here, but I'm also an outsider for these climate research labs that I'm visiting. And I thought that was an interesting perspective, because I'm not writing, or at least when I started the book, I wasn't writing as an expert. I don't describe myself as a climate scientist. Although increasingly now I'm asked by journalists to talk as a climate scientist, because I've learnt so much of the field. So in the book, I've woven through my descriptions of these models and the work that goes on in these labs with my own story, kind of coming into this world, being curious about what they do. And I in the book, I use that as a hook. I think for me, it worked really well. It took me a while as an academic to figure out how I write like this. Academics don't write about themselves. They write about the science they're doing. But I had to keep reminding myself, tell the story of how I discovered this thing. So that's the perspective in the book. And I hope it works to make the science come alive. The other thing that I tried to do in the book a lot was introduce some of the people that I'd met along the way. So I've interviewed more than 50 climate scientists while doing the research for the book. But I put some of them into the book, and I describe who I met, how I met them, and a little bit about the work they're doing to try and bring the science alive.
Right. And you've been able to do that. But one of the things, when I started speaking to people about the fact that I'm going to be interviewing you, and I had read the book, and as I told you, I have some insight into this world. But what I realized very fast is that nobody quite really understands what climate models are. Now that we have you here,
yeah,
what is a climate model?
Yeah, and that was that was the reason for writing the book, and also the struggle for why it took so long. So they're incredibly interesting things. And one of the things I realized very early is the word model means all sorts of different things to different research communities. So
Yes.
to a statistician, a model is essentially a summary of a very large complex data set. When talk about what computer scientists mean by model, we have all sorts of different understandings of the word model, but the climate models I am talking about, these are largely put together by physicists, and for them a model is a simulation of complex physical processes. So in order to build, so these are global climate models, they represent the entire globe. And what today's models do is that they couple together a number of different subsystems. So you'll build a simulation of the atmosphere, you'll build a simulation of the ocean, build a simulation of what goes on land surfaces, so plant growth, carbon cycles, soils, flow of water, and so on. And then plug in other things like atmospheric chemistry, the change of how gases decompose in the atmosphere, the chemical reactions that go on, or ice sheets, how ice sheets grow and retreat. So they're all physics-based simulations. And then for me, the what I really try to do, and I get to this about the middle of the book, is drill down and understand if you had to build a simulation of the atmosphere, what would it do? And I realized, so the way that they approach this in these climate models is, first of all, you impose a grid structure on the planet, and that in itself is a challenge because the planet is it's a sphere. Well, it's not even quite a sphere; it's a slightly distorted sphere. So what you do is you impose this grid, and the grid points might be, say, quite far apart. They might be 30 kilometers apart, but that still gives you hundreds of thousands of grid points across the whole surface of the planet. And then you figure out the equations of motion, and the first set of equations are derived from Newton's laws. So, force equals mass times acceleration. Any mass of air that's moving will continue to move unless another force acts upon it. And you put in things like the force of gravity, the Coriolis force, which is the rotation of the planet, and force from air pressure. So air in upper layers pushes down on the air in the lower layers. And so then what you're doing at each grid point is you're solving a whole set of equations, and these are partial differential equations that capture all of how all of these quantities change over time. And then you just run the simulation forward in time. So a typical time step in one of these models might be 1 hour, 3 hours, something like that. So at every grid point, in every hour of the simulation, you calculate using all of these equations what the next set of quantities are at each grid point, and then you just keep iterating. And you might run the model forward for a few years, or you might run it for an entire century. If you want to do that at a reasonable high resolution for the entire planet, you're going to need a supercomputer, and it might take you a few months on a supercomputer to run the full simulation. So these are really stretching the capabilities of the fastest machines. And then what pops out, if you get it right, are all the patterns that we see around the planet. So the patterns of winds, the patterns of the seasons, the patterns of rainy seasons, dry seasons, different parts of the world. So if you get all the physics right, all those patterns are sort of an emergent property of connecting everything together.
Right. Thank you. But that's one kind of a model. And in your book, you start from Svante Arrhenius and his, let's put it like this, at that point of time, disreputable chemistry thesis. And then you come to the new one. So how many different kinds of models are there?
Yeah, there are lots. That's a kind of another part of the story that's rich and complex and interesting to tell. So Arrhenius's model was very simple. So this was a scientist who was working at the end of the 19th century and asking questions about what caused the ice ages. And his hypothesis is it's a reduction in carbon dioxide in the atmosphere that could have caused the ice ages. And of course, this is actually, when we think about it now, for a 19th century scientist, it's quite a surprising hypothesis. So I spend some time in the book talking about where did that even come from? How did he even come up with that idea? And of course, it turns out the greenhouse effect has been known throughout the 19th century, and the experimental work to prove the properties of these greenhouse gases was done in the 1850s. So what he did, his colleagues all thought he was crazy. Like, there's no way carbon dioxide in the atmosphere would change, and if it did, it wouldn't cause the kind of cooling that we saw in the ice ages. So he set out to prove it. He spent about a year doing all these hand calculations, no computers at the time. Actually, it amuses me, back in those days, the word computer in the English language used to mean a person that does calculations for you.
Yes.
So the way his model works is, he said the crucial equation that captures how the temperature of the planet reacts to changes in greenhouse gases is an energy balance at the top of the atmosphere. So he says, essentially, if you want a stable climate, incoming energy from the sun must equal outgoing energy lost from the planet back to space. And if those two quantities aren't equal, then the temperature of the planet must warm up or cool down until they are. A stable climate can only arise from a balanced equation. So I tell my finance colleagues it's like balancing the books. Then he uses some existing work on equations for how a warm body radiates heat to its surroundings. So if there are any physicists here, they'll know that's the Stefan-Boltzmann equation is the key equation that relates for anything that's warmer than its surroundings, at what rate does it radiate? And it's related to its temperature. The hotter an object is, the faster it radiates heat. So he says the Earth itself is a warm body floating in space. It radiates heat in all directions, and it radiates it in the form of this infrared heat. The Earth is not very warm, so it's infrared. A very, very hot thing like the sun radiates more in the visible spectrum. So he does a whole bunch of work. He's got this wonderful data set from Samuel Langley, who a couple of decades previously had spent 6 or 7 years measuring infrared from the moon. He was trying to measure the temperature of the moon with this instrument that he'd invented that could measure across the infrared spectrum from a distant body, and it could tell you its temperature. So what he's done is he's looked at the moon at different heights in the sky throughout the years, and he's measured the infrared rays across this infrared spectrum. And he's also written down things like the local weather conditions when he made the measurements, the humidity of the air, and things like this. And what Arrhenius does is he takes that data set and he turns it into a set of coefficients for how much, as that infrared from the moon passes down through the atmosphere, how much of the infrared is absorbed by the two gases that he focuses on, carbon dioxide and water vapor. And water vapor is also a strong greenhouse gas. But because these measurements were taken at different times in different humidities, moon at different heights of the sky, so the rays have passed through different thicknesses of atmosphere, he's got the variability he needs to isolate the effect of the two variables. And he puts all of that into the model and comes up with this answer, which is that if you reduced carbon dioxide by about 2/3 of the quantity it was back then, that would give you the temperature difference you needed to explain the ice ages. And then he asks the other question, what if there was more carbon dioxide? He says, I realize, industrial era has just got going. We're building lots of coal-fired, we're using coal for all sorts of energy, and that releases carbon. What if there was more carbon in the atmosphere? And he says, if we doubled the carbon dioxide, that would lead to a warming of about 5 or 6 degrees. And so it's really just this one equation, this energy balance at the top of the atmosphere. It's an equilibrium model.
Right.
And he just works out what the new temperature would be for any quantity of carbon dioxide.
And he keeps on adding, and then there is not really a consensus. And then in 1970s, these things are rediscovered. So essentially, one of the challenges, if I were to put it to you like this, we all hear a lot about climate change everywhere, and climate change and the fact that climate change is being caused by human beings is not in a doubt, except amongst a very loud, small subset of people.
Mm-hmm.
And their contention is, how do you know that your maths is right? And I'm actually going to, at some point of time, because I'm an economist and we love creating controversies, I'm going to create some controversy by citing a gentleman you might have heard of, you might not have heard of, Steve Koonin.
Oh, yes. Okay. I've come across Steve's work. Yes.
Right. But that's for the later. I was speaking to a software engineer, and the software engineer was not really convinced about climate models. And he said, look, all of this is fine, but what goes in is what goes out. He used garbage in, garbage out. And that to me is a very simplistic way of looking at these extremely complicated models. I think you write in the book that if one were to print it out, it'll be on 18,000 pages at a minimum, right? So what goes in this climate model, and how have things, because in the book, there are sections after sections where you name people, IMP and so on and so forth. But one of the things is that ocean drives climate change. And that only enters the picture very, very late. So can you tell us what all is going into a new climate model now? What is the input?
Yeah.
The output?
Yeah, absolutely. So the story, after Arrhenius did this work, he was largely ignored for more than 50 years. And partly, I think what happened is what the work that he did was so complex to do, nobody else wanted to attempt it to kind of repeat his work. And we know that replication in science is really important. And a few other contemporaries of his published work that they said they don't think what he's saying could possibly be true, and here's some experiments that we think disprove it. So just like today's scientists face people saying, no, we don't think you're right, and here's why. But because nobody else was willing to do the modeling, his work was ignored. And it wasn't really till the birth of modern computing and the birth of modern weather forecasting that things pick up again. So 1950s, with these new electronic computers that are around, people say, well, we can start to take those equations that I talked about and actually compute with them and kind of compute the weather. So that the focus in the 50s was computing the weather. And then we get to the point in the 1960s where people say you could take a weather model and run it for the whole planet for a much longer period of time and calculate kind of stable weather patterns. And that was the focus of that works. What are stable weather patterns? But as you say, these are still just the atmosphere. So it's wind speed, humidity, air pressure, kind of those variables that we're used to in our weather forecasts that they're computing. But then it kind of in parallel, people are working on ocean models, and an ocean model does almost exactly the same thing as an atmosphere model with the same equations. It's the same physics. The motions of water in the oceans are driven by the same physics. So you take the same set of equations. Now, water behaves a little different. It's much more dense. It doesn't compress like air does. So you've got to make a few changes to those equations. But essentially, if you do that, you can build an ocean model in exactly the same way as you build the atmosphere model. And then the fun starts when you try to couple them together. So I've got a whole section in the book where I describe, and this was really first done in the 1970s, when you couple an atmosphere and ocean model together. And the reason why you want to do that is because you want to understand how heat moves between the two. Right. So both the atmosphere and the ocean act as heat pumps. They move heat around the planet. And they do it in different ways. They move heat at different speeds to different parts of the planet. And if you don't have them both, you'll miss kind of how the layout of different climates in different parts of the world work. You'll miss the overriding factor here is that the planet receives a lot more heat in the equatorial regions, and it loses a lot of heat by the poles.
Right.
And the atmosphere and the oceans kind of transport the heat from the equator, move it north and south towards the poles, and then a lot of it is lost to space in the polar regions. So if you want the whole thing, you've got to get all of that dynamics in. And they coupled these models together. And what they found was if you've got an atmosphere model that's tested on its own and can simulate the atmosphere well, and can simulate like what's happened over a period of time. Let's see what happened over the last 100 years. And you say, oh, I've got an atmosphere model and I'm getting it right. And the same with the ocean model. You build the ocean model and say, I can simulate ocean currents as they have been observed over the last 100 years. And you put them together and then the two models mess each other up.
Right.
And it's really interesting way. It took scientists nearly 20 years to figure out why, if you take a fully tested atmosphere model and a fully tested ocean model, stick them together so the software interface is the surface of the ocean. So heat passes up and down. A few other things pass up and down. For example, some greenhouse gases are absorbed by the surface layer of the ocean. So there's a little bit of exchange of heat and mass between the two. And of course, what happens and what they eventually discovered is if you've tested your atmosphere model on its own, you're testing it in the absence of a dynamic ocean. There's no ocean kind of also moving heat around. So you have to put in some parameters that adjust for the absence of the ocean to kind of make up for the ocean not being there doing its thing in order to simulate what happened in the observational data set. And the same with the ocean. If you've tested the ocean on its own without an atmosphere, you've got to put in some compensation mechanisms to say the atmosphere is not there doing its thing. And it took them a while to get out of the mindset of I've tested this thing on its own and therefore it's correct, to, oh, wait a minute, no, it's a partial view of the world and there are compensatory factors in here for the things that are missing. And if you put the two of them together, you've got to go into all of those parameters that you've put in, and you've got to adjust them again for the fact that now, no, the thing that was missing is no longer missing. It's there talking to me, doing its thing. So it wasn't really until the 1990s that we ended up with these coupled atmosphere ocean models with no kind of artificial adjustment. So now just going back purely to the equations. You know, as I said, it's largely Newton's equations. There's a few other things, but just going back to the pure equations without these other adjustment factors. And then finally, we have now a stable simulation of what the planet does that's able to do, and this is what really blows my mind, it's able to simulate the distant past. So the period of the Earth when we were going through these cycles of ice ages, you can simulate those in these models. You can simulate the 20th century and see the warming that we saw, especially towards the end of the century. And then you can run the model forward in time and project future climate change. And it's all the same model. You're just setting up the circumstances that were observed, letting the model run and seeing how the atmospheres and oceans behave. And then since about 2000, people have started adding in all of these other things. They add in a dynamic ice sheet so that we can see over the course of a year how ice sheets grow and shrink. So sea ice and glaciers on mountains. They've added in river routing models to show, you know, when rainfall falls on the land, where does the water go? And then you want to capture correctly that the water flows to the right ocean basins. Some of it evaporates, some of it's captured in the soil. And you want to get all that balance right. Then they've got on the land surface, in each grid cell of the model, you'll have a representation of the mix of plants that are found in that part of the world. And then how those plants behave, how they grow in the spring and summer seasons, how leaves fall off and decompose in winter seasons, how those plants hold moisture or water evaporates off the leaves into the atmosphere again, how a plant changes what's going on in terms of energy on the planet, because a region that's bare of plants will absorb more heat in the soil than if you've got shady trees above protecting the soil from the sun. So all of that is put into these land surface models as well to get the complexity of what goes on.
And that makes it very interesting. And this is like, I have a question around this, but who what is the team that is making the model? Because when you start your book, it's physics, mathematics, and
Yeah.
then by the time your book ends, there is a team of software engineers. There are people. You talk about the IMD supercomputer Cray XC40, and there is a team that is just running that. So, who are the people? What are the teams that are making these models now? How have they evolved?
Yeah, so now I would characterize them, I think, as Earth system science teams. And that name actually is increasingly used for the models. The scientists themselves tend not to call them climate models anymore. They tend to call them Earth system models, just to capture all of these other things that have been brought into the models. So these are very large interdisciplinary teams. So a typical one of these models might have 50 to 100 people contributing code to the model over time from all sorts of different disciplines. So, if you're bringing in the plants, you need the biologists. If you're bringing in soil, you need soil scientists. If you're bringing in the oceans, you need the oceanographers. You need the chemists to capture some of the chemical reactions that are going on. And so they're all working on their piece. And some of these models are run standalone. So if you're, let's say you're an atmospheric chemist, you'll build a model of what goes on in these chemical reactions in the atmosphere and run it for your own experiments just on its own. But you can also take that model that you've built and couple it to one of these Earth system models to study the interactions. Because then you might be interested in, well, I understand how the chemistry works in the atmosphere now, but if the climate changed, how would those chemical reactions change? And so you want to see it in this coupled system as well. So one of the things I describe in the model is I think of these big models now as actually one of the chapter titles is the well-equipped physics lab. It's like having an entire lab available to you that you can bring your experiment in and run it with all of the other equipment provided. You're focusing on your piece. You say, I just want to study this piece here, but I want to study it in the context of the global climate system. And so you plug in your piece and you run it in the context of the whole model. So very large teams, very interdisciplinary teams. And then certainly over the last 20 years, an increasing team of software engineers who act as support to the scientists. Because now as you build these things and test them, the amount of work needed, you make a small change and you test it. For anyone that's built complex software, it's easy to mess things up. So the testing process itself becomes a massive exercise. And so you have a team of maybe 10, 15 software engineers helping the scientists, kind of keeping them honest, running the model every night with the latest changes, running a whole series of standard test cases to make sure that they're not breaking anything, something that already worked in the model and was shown to work, that today's changes haven't broken it.
Right. So that one of the fascinating things that comes up in the book is that you, as we also talked about it, you started your career, if I'm not wrong, in NASA, right? You were responsible for code, and this is absolutely something that I had not thought about before at all, and it is wonderful to know that for every 1,000 lines of code, you have a very, very small error. I think you put it at 40. So 40 errors, and that's a very, very small error, right?
That was so that number's from the space shuttle. So
Yeah.
the space shuttle has the lowest number of errors per 1,000 lines of code that's ever been measured.
Right.
It's actually less than 1 per 1,000 lines of code. The space shuttle software was about 400,000 lines of code in total. So that gives you about 40 errors
40
in
errors,
total.
yes. Yeah.
But now remember, this is the flight software that controls the space shuttle. A lot of the flight of the space shuttle, the astronauts might get to steer, but most of the other stuff, the software is doing the work. So incredibly difficult task.
Right.
Launch it, do the orbital maneuvers, and bring it back down to land. So
Right.
40 software errors in the entire, how long did the space shuttle program last? 20 years.
20 years.
40 software errors in the entire 20 years of the space shuttle program it's an impressive achievement, but it's not perfect, and that's really interesting.
And that is the thing that I was coming to. So you are responsible for that particular program. And then you come to something which is very dynamic. It's chaotic. So as you said, it is a self-reinforcing thing. It has a
Yeah.
pattern emerges, and you can't control the pattern. So talk about that transition, because that is very clear in the book. But I think also a lot of people who look at climate models as black boxes, and these are black boxes. You and I, or anybody else who's working on them, they have no control. But how the black box is made, the teams that are working on it,
Yeah.
the kind of what are the kind of experiments that are being done? That's one question. And second, what are the caveats of
Right.
being a model? Because that is something that you do talk about.
Yes, absolutely. So I use the space shuttle software and some other examples from NASA kind of as an analogy here. So if you're building these very high demand safety critical systems, and it's true anywhere where we have software in a truly critical setting, you know, it's impossible to guarantee the software does not contain errors. You know, humans are humans. And so what engineers do is they have a whole series of additional layers of what they call safety assurance that stop those errors causing a disaster. And some of it is some of it's the engineering practices, the idea that you have lots of reviews. You test the software, that's one layer. You have code reviews, you have experts sitting, looking at the code, kind of walking through it together, arguing about what might be happening. So that's a code review. You have different kinds of testing. You test individual pieces, you test the entire end-to-end system. You have problem tracking systems. If anybody spots something weird that they think shouldn't be happening, you log it in your problem tracking system, and then there's follow-up that has to happen, and then you can eventually close the ticket once you've resolved the problem. That's another layer of protection, because it means if somebody does spot something, it's logged and there's a record that it happened. It's not like we're ignoring weird things that happened that we're just hoping might be okay. You never just hope it's okay, you investigate. Being open about the errors, so communicating across the teams is crucial. So there's all these kind of engineering practices that layer on top of just writing program code that ensure that even when we do make mistakes, someone somewhere along the line catches it. And one of the things that very few people ever knew about the space shuttle actually had five different flight control computers on board, 4 of which were programmed with the same software, and 1 which had software written by an entirely different team. And the idea is if one of those computers goes wrong, one of the others can take over. So you've got this very redundant system. So there's this redundancy built in as well. And what I was looking for then with the climate scientists is to say, do they have a similar set of layers like that would prevent an error in the model causing with the shuttle, we kind of know what happens when something goes wrong. Okay, but what goes wrong with science? Well, one would be somebody publishes a paper in which the results are wrong because of an error in the model. Or with respect to climate change, as that science gets translated into climate policy, maybe we've misled the policymakers because there's an error in the model. And so what I was looking for is, what are the protections? How do we make sure that errors that are bound to creep in the models just because of their complexity don't make it all the way through to published science or to guidance to policymakers? And what I found is really amazing. The scientists have all of these extra levels of error correction, just like NASA would. And they've kind of arisen over time just by the scientists thinking deeply about what they're doing. So one is they use just the mechanics of science itself as a protection. So the idea of peer review, for example, when we publish our papers, they go off to 2 or 3 peers who review the paper, before it could be accepted for publication. Well, they're doing that with the model changes as well. So let's say you're one of these modelers, you make a small change to the model because you think it might improve how the model simulates, let's say the cycle of the monsoons. And you run an experiment. So you set this up as a controlled experiment. You say, here's the old model, that's my baseline. Here's my new experimental version where I think I can get a better simulation, let's say, of the timing of the onset of the monsoon season. And now I've got a controlled experiment. I've got a hypothesis, and I'll do all the statistical analysis of the results from the model to say, did I see what I expected to see in the model? In other words, is my hypothesis correct? And then if it is, it goes through 2 or 3 levels of review from the other scientists in the lab to say, yeah, okay, you set up the experiment, you've run everything correctly. We're convinced that that does improve the model. And then, eventually it'll be accepted to be included in the next version of the model that's released for everybody else to use. So they're using the mechanics of science itself as a layer of protection on this work. And then the other thing that I think is truly amazing is the redundancy. So I talked about on the space shuttle, five different computers, right? In climate science, the equivalent to that is we have more than 30 different research labs around the world, in all sorts of different countries, building their own version of these models. So completely independently, creating their own one of these models. And then they all get together periodically and run exactly the same experiments on all their models, submit all the results to a public database, and let every scientist in the world have access to them. So anybody can see all of the results of all of these models. So it gives them a way of comparing the models on a standard set of kind of benchmark experiments. So that then does the replication side of these things. So we're never relying on one model. We're relying on maybe 30 different models of the same thing to explore what we know and what we don't know. So the models kind of give us some sense of the range of uncertainty, because the models do disagree on some of the details. They agree on the basics. They agree that, if you add carbon dioxide to the atmosphere, the planet warms. They agree roughly where the warming occurs, and they agree with how then that disrupts weather patterns. But then if you wanted to say, I'm interested in a particular city, how will that be affected by climate change? There might be disagreements between these models about, for example, well, how would it change rainfall? Is it increased rainfall? Is it decreased rainfall? And the models might disagree in a particular region about how that would play out. So then that tells us, okay, this is an area where we're less certain of exactly how things would happen. So the models kind of give us that sense of, here's the things that we are sure about, and here's the things where we think there's still some work to be done, where we need to do more investigation.
Right. So this in 2008, 7-8, we had financial crisis. One of the things at that point of time was that the financial crisis was largely perpetrated by models and modelers in a way. So I'm now taking you back, and this is taking you away from the book, but it's pertinent to that, because at that point of time, I was still in school, as in college, and I was trying to figure it out. I was trying to figure out, do I want to be an investment banker or do I want to be a scientist, right? I was trying to, because I could model. So, and I came across this series of essays, which then later got turned into a book by Emmanuel Derman. It was Models Behaving Badly. And it's one of the books that I still look up to. And one very important point that Emmanuel Derman makes is that financial models have no basis in reality. Nobody is going out and validating them. Nobody, when you say that a CDO is worth X amount of money, it's not a law of nature. But if you say that CO2 introduced into the atmosphere is going to do this, it could possibly be 0.1 degree less or 0.3 degree more, but it's a law of nature. And yet, more I read about this world, and especially while I was reading your book, although there's not a lot of application of mathematics in this, which is great. But then I started reading, stuff online, the internet,
Mhm.
and that's where the engines kind of fall off. Because then you kind of have these things about, okay, so who is validating these models in the real world? And you just made a very interesting point about uh, X number of models, and they are all having an argument with each other. Tell us a bit about what kind of experiments are people doing on these models, because you refer quite a lot to experiments on the models that are being made. And B, how do you take this wonderful piece of computer code and go and see how it behaves in the real world?
Yes, exactly. So in parallel with all this modeling work, of course, there is a massive amount of effort around the world to collect data. So we have, thousands of satellites kind of observing the planet and how it changes over time, measuring different quantities at the surface and in the atmosphere. We have, systems of weather stations around the world that record all the local conditions going on with the weather. We have systems of buoys out in the oceans that measure ocean currents and temperatures. And all that data is collected. So that gives us, NASA now calls that the Earth Observation System. It's a massive effort to observe what actually happens on planet Earth. And certainly, the satellite era really started 1970s, particularly the 1980s, flying enough satellites to give us good eyes on the planet. So that means for the last 30 or 40 years, we have really good data about what actually happened. So a crucial test for your climate model is, can you simulate exactly what happened over that period, that we have these really good, really detailed observations? And so you set up the kind of conditions, like what were the quantities of greenhouse gases in the atmosphere over that period. And you run the model and you see if it can simulate. And the answer is yes, actually, the models do a really good job of simulating what we've observed in the past. So, and that's a practice that comes from weather forecasting. The weather forecasters call that a hindcast. You do a kind of forecast of conditions that already happened, and so you already know what the results are. But you're not giving the model the results. You're running the model. You're telling it these were the conditions. Can the model then tell you what happened over that period of time? And that's done all the time by all these different labs. They're always running these kind of hindcasts to say, is the model continuing to correctly reconstruct some period of the past that was observed? The paleoclimatologists, so these are the people that study climate changes in distant history, long before humans were around. They'll also run a hindcast, but they're interested over a period of, let's say, 100,000 years or 1,000,000 years. Can the climate model simulate changes of climate that we see in the fossil record? And we know we have less data, of course, but we know, broadly speaking, when the planet was warmer, when it was colder, how different heights of the sea, for example, the seas have been at different heights. Can the model simulate all of that? So it's a very different test to the last 30 years, very different conditions on planet Earth. So can the model simulate that as well? Can the model then get right specific things like, let's say, the hurricane season in the Atlantic? So the hurricane season in the Atlantic starts typically July, August, and runs through to December, and it's driven by warm water in the equatorial regions, actually just outside the equatorial regions of the Atlantic. And so you run the model and you say, does it get hurricanes right? Not each individual hurricane, because that's a weather forecasting problem, but the pattern of hurricanes over the season. The fact the season starts at a certain time of year, you might observe a certain number of hurricanes of a certain strength, and they tend to have different paths that they follow. So are you getting the overall statistics of hurricanes right over the course of a season? Or one of my other favorite ones is, can you simulate the action of a volcano? So when a large volcano erupts, it releases a huge amount of dust into the upper atmosphere, and that has a cooling effect that blocks the sunlight. So if you look at the kind of temperature records for the planet, when a big volcano goes off, you can see for about a year or two after that volcanic eruption, you can actually see a drop in global temperature, and then it slowly recovers. So again, you do that test in the climate model. You say, okay, I'm going to insert an artificial volcano into the climate model at this particular location. And it does the following thing. It adds the following gases and dust to the atmosphere. Does the climate model then mimic the cooling effect and then the gradual recovery that we see in the real world? And the answer is these models get all of these things right. So that each of one of these tests gives us a bit more confidence that we've captured these core and very complex physical processes.
But there are outliers, right? For example,
Yeah.
I'm now referring to a study that was just published, 7th November 2023. This came out in Nature Geosciences, and I'm going to get some of the words wrong, so please bear with me. Early Eocene low orography and high methane enhance Arctic warming via polar stratospheric clouds. I didn't understand a lot of the paper, but what I did understand was that these were areas with high greenhouse gases at a point of time, and perhaps climate models have been able to have not been able to do fair justice to them. And isn't that a worry for outliers?
Yeah, I mean, there'll always be outliers. So the scientists talk a lot about the fact that their models should be better, and they always acknowledge it. They say, you know, any model, but the fact that we call it a model, it's different from the real world. It's a simplification. So there are always processes that are missing. And so the work of these scientists, I think one of the things, certainly I had this idea before I first started studying this, that the goal of the scientists is to predict future climate change. It's not. That's not why they build the models. The reason they build the models is because they want to study what we know and what we don't know about these complex processes. And so they're always trying to say, okay, well, the model captures this, but it doesn't get that thing right. So how would I then improve the model to capture that thing right? And so then that becomes a particular study at that lab to say, I can see the model's getting this wrong. Why is it getting it wrong? And what do we need to do to improve the model? That also means that kind of when we take the results of the models and interpret them for other audiences, where the scientists are also kind of adding their expertise to say these aspects of, let's say, of future climate change, we've studied very thoroughly, we've tested them, the models do really well on. These other aspects are areas where we know there's still some work to be done and where there's still some uncertainty. And so they're kind of describing that as well. You know, when they publish a model result, they're describing that wisdom they have from all of the testing. And as you say, there are some conditions on planet Earth that the models don't do such a good job of. And so they'll describe that as well and say, don't look at this particular aspect of what the model's doing. We're worried that that might not be accurate. And so you can kind of separate these things. So for example, surface temperatures over the 20th and 21st century, we're pretty sure that the models get absolutely right. And they've been proven over and over again to get absolutely right. Rainfall patterns, the models are reasonably good on, but nowhere near as accurate as they are with predicting temperature. So we'd say, okay, take changes in rainfall, especially as climate change gets more extreme, take what the model says about changes in rainfall with a bit more of a grain of salt. There's some more work to be done there. It's not so clear. And then the further you get away from recent climate, so 20th century, which is very well observed, we have lots of data. 21st century with climate change kind of emerging as a key signal, what we've seen so far and perhaps what we might see over the next few decades, we can be reasonably confident. But go back a million years when the planet was a very different temperature, the land masses were arranged differently, then there's more uncertainty. You say, okay, well, the models are getting some of those pieces wrong. But every time the scientists talk about that and they publish the papers that say, yeah, here's an area that the model's not doing, that just becomes another scientific study to say, okay, well, how can we fix up the models and get that right in the model? And then the models just continually improve over time.
Right. But so we are now headed towards the 1 hour zone, and then I also have to open it up to people here.
Sure,
So I'm
absolutely.
going to ask you last 3 questions and then open it up. And if there are not enough questions, then I've got a whole lot of questions lined up.
Sure.
But here's the, so you actually refer to it, but you don't really talk about it in the book, about bias.
Yes.
There are different institutions, they are all working at it. You kind of talk about different institutions, like there is a French system, which is different from the German system. German system is part of a university and the Max Planck Institute. The French system is a composite of a federated model, which is a very interesting way of looking at it. The Brits are doing their own thing, largely under the Met, that is the weather office. So they have an immediate concern that they have to solve. How do these different institutions, different models, how do they treat for bias? And this is something that I was very interested in finding out from you.
Yeah, and bias itself is awkward because, again, the word means different things in different communities. So I think, I mean, the way that we might think about bias, especially kind of as outsiders looking at a field of science, is, and I think this is how you're intending it in the question, is, are there blindnesses perhaps that this group of scientists haven't realized, and they're kind of making a systematic set of errors in how they understand the world and get that into their models? So that's one kind of bias.
Deviations, largely.
Yeah. Now the climate scientists use bias in a completely different way. Bias to them is data that they've collected, observational data that they've collected about the real world. Does it reflect the actual numbers that they were trying to measure? So in a temperature measurement, how off is that measurement from the real temperature of the thing that you're trying to measure? So that's a different kind of bias. That's bias in the data sets. But I mean, in some sense, all of these things mean, are we getting it wrong? You know, where are there places where not only we're getting it wrong, but we don't realize we're getting it wrong? That's the crucial thing. I talked about all these layers of protection. If you've measured the amount of error and you've understood it, and you can talk about, yeah, we know this is a place where the model's getting it wrong, then I don't worry about that. But I think your question is really getting about the, I guess, comes back to that very famous quote from Donald Rumsfeld, the unknown unknowns.
The unknown.
What do we not know that we don't know?
Yeah.
And that I think is the real, that's a worry with any field of science. Like, where are there surprises where we should have known this thing and we didn't? And why didn't we know it? Now, you can't ever eliminate the possibility that that's creeping in somewhere. But with the climate scientists, the fact that, I mean, as you said, there's these different labs around the world, and they've actually got different goals. They're not trying to do exactly the same thing. Each of them are trying to do something different with their models. And so they've got different kinds of expertise at their labs. So the UK Met Office, for example, which is one of the big models that I've studied, they run that model it is the same model. They run that every day to do their weather forecasting. And the climate scientists use the same model to do these really long climate simulations. So that allows them to eliminate one kind of bias, which is, can the model simulate day-to-day weather accurately? It's no good getting the global climate right if, you know, on a day-to-day basis, the model just wouldn't be able to simulate correct weather conditions. The French lab you talked about, they tend to focus more on climates of the distant past. So the paleoclimate work. So they want to know, you know, can the model simulate these over many millions of years, these large changes of climate that happened before humans were around. So each of them is coming at this research from a different angle. They end up building models that can do the same kinds of experiments, but they focused on different aspects where a bias might creep in. So collectively, they've kind of tackled this bias question by having different questions, by being different. And it's that diversity that I think gives us a lot more confidence that the biases aren't creeping in. Where bias in a scientific community really becomes a problem is if everybody's doing the same thing and making the same assumptions. If you all make the same assumptions and those assumptions turn out to be wrong, you've got a huge big problem. But that's not really what goes on in climate science, because they're all doing such different things and asking these very different questions. So that's how you deal with bias in a scientific community.
Right. There's actually a lot more that we can get into it, because this is a very interesting topic, but we leave it for now.
Sure.
One of the things that is fascinating in the book is the sheer amount of resources that have increased, the amount of people that have increased, the labs that you talk about, some of the photographs in the book. These are fascinating. As an economist and somebody who has to look at it from, in our country, we have a budgetary office and we have the annual budget. I'm pretty sure that's the same for Canada. Science and climate change, although cool things, everybody talks about them, but there are funding cuts. Universities don't have money. If you want to study paleo history or paleoclimate, then where is the money going to come from? So in this day and age, when climate is one of the most important topics, and there is a COP22 around the corner where there are going to be a whole lot of things that are going to happen, how do you see the funding landscape, especially around, I'm talking about a global thing, not necessarily about Canada or India,
yeah.
but the models are becoming larger. Resources required are going to be much more. It's a very resource intensive thing. You need more people, you need more human resources. And yet climate resources are all over the place, facing funding shortages. So just your comments, not a question specifically, just your comments. Something I've wanted to understand for some time.
Yeah, I mean, this is, in some sense, this work is it's big science. So these are, I mean, the stuff that we see in the newspapers, about particle physics, or big astronomy with all the, the big new telescopes and stuff. It's work on a par with that. It is expensive to do, and the funding has to compete with other branches of science that also want to do big ambitious things. So most of the modeling work that I talk about in the book actually isn't even done at universities. University professors can't afford to do this. You can't get grants that are big enough to build your own climate model on the scale that we're talking about for some of these models. So they're largely done at government labs. And so certainly many countries now have kind of government science labs funded by their federal government, building their own climate models, doing this work, maybe on a very large supercomputer. And then, of course, what happens is the funding goes through cycles. So I was out last week, by coincidence. I went back to NCAR in Boulder, Colorado, which is one of my studies in the book. I was back there, and they were moaning that the Europeans have much more funding than they do. There've been budget cuts in the US over the past few years for this kind of science. And they were saying, there's things that they want to do that they can't do. And the Europeans are getting ahead because the European Union is much better at funding this kind of science than others. So, I mean, one answer to your question is funding cycles for any kind of scientific work kind of come and go. Funding agencies get excited about different things at different times. And over the whole international community, those things maybe balance out. So if one country like the US is cutting back, other countries might step up to the plate and do more work. So that helps. The other thing, of course, that helps the funding is the importance of this work, with, as you said, with the COP processes, with the importance of international agreement on climate policy, and more demand from the policymakers to answer more specific questions about climate impacts. That pushes the funding agencies to say, well, of course we have to fund this work. It's crucial to feed into that policymaking process. So I don't see big challenges with funding because government's saying, we just can't afford it. It's one of these things where you almost say you can't afford not to do this work because of its importance. But that doesn't mean, like all science, there are challenges, that there are things that these scientists would love to do that they don't have enough funding for.
Right. So last question before I open it up to everybody else. We've already started getting in some questions. And as I promised everybody, controversy has to be created because,
Okay.
So Stephen Koonin is a former Undersecretary for Science of the Department of Energy in Obama administration, not Trump, Obama. Not on the loony side of the United States spectrum yet. He wrote a book which came out 2 years ago, and it was Unsettled: What Climate Science Tells Us, What It Doesn't, and Why It Matters. One of the things is that he called almost all of these, and this guy is actually a very interesting person. He's a physicist, former provost of Caltech. So he knows what he's talking about when it comes to models. And yet, I'm now quoting from the book. Heat waves in the US are now no more common than they were in 1900, and that the warmest temperatures in the US have not risen in the past 50 years, right? And if you read the book, I read both the books together, and I came away very confused, right? Because I read this one book and I was like, yes, climate models, they make sense. We have to, care about them. The pay model, the GCMs, the CMIP, all of that is great. And the other book, equally convincing if you just read the book, right? If you don't then go and look at IPCC. Models can be interpreted. One of the things about models is, and being an economist, that thing becomes very clear, is that you have a thing that you can argue on both the sides. When it comes to climate science, how easy or hard do you think it is to make a case for something just on the basis of, say, so models are wrong because, they can't forecast X, Y, Z. They have not been able to do it historically. One of the points that he makes in the book is that models, and he is quoting a study that I don't see it in front of me, although I'd written it. He talks about Greenland and then says that models, only 40% of the models are correct, 60% of the models are wrong, because they kind of race towards a greater temperature increase when you increase CO2, right?
Right.
And this is something then I looked up. There is a very interesting episode that he recorded, like we are recording here, but he recorded it with Hoover Institution, with Peter Robinson, who is also a very serious communicator, right? And he an op-ed for it in WSJ. And if it bleeds, then it leads in the news world, right? So there is that whole thing. So my question is, how do you actually argue against this?
I've met Steve Koonin. I've had dinner with him. He came to visit University of Toronto a few years ago. This is before his book came out.
Right.
And I wanted to get a sense of where he comes from and how he thinks. And the thing that alarmed me in my conversations with him is he has never visited one of these climate modeling labs. He has never sat down with the modelers and talked to them about what they're doing. So he's relying on kind of second and third hand information. He hasn't actually gone and done the studies of what are these models and what they're doing. And that really worries me. The idea that you can publish a book without doing that research, I think, is deeply worrying. And so he's relying on information that he's read that's critical of the models. And of course, as I said, we know there are things that the model doesn't get right. So if he quotes a number to say, not sure exactly what the variable was, but let's say 60% of the models get this wrong. There are areas where we know that's the case, that there's a specific process in the atmosphere, for example, that the models aren't getting right. when I visited, I talked a little bit earlier about the monsoons. When I visited the UK Met Office the first time I went there in 2008, they were really frustrated because they couldn't simulate the Indian monsoons correctly. And they knew they were getting it wrong, and they were completely open about it. They'd publish papers to say, we're getting this wrong. And so Steve Koonin would look at that and say, oh, these papers are admitting they're getting it wrong. And I look at that and say, this is open and transparent science. They're being very honest about the weaknesses in the models. If they were covering it up, if those papers didn't exist and there's flaws in the models, that would be truly worrying. And I never found any cases like that. All of the cases that I found when I chatted to the scientists, get into their labs, sat in on their meetings, I found complete transparency about the weaknesses in the models and a desire to publish that so that the world knows this is what we can do, this is what we can't do. And so Steve Koonin comes along and he picks up these and he takes them as evidence that the models don't work. And I take this as evidence to say, no, this means not only do they do work, but we know exactly when they work and we know exactly when they don't work. And the question is, are we applying them to questions, especially around the policy making? Are we applying them to questions where we can be confident that the models do give us good answers? Or are we applying them to questions where those answers might be flawed? And so the issue comes down to, what are you asking of the models when you want them to answer questions about the real world? Is it areas where we can be confident that they are correct, or is it in these areas that are still problematic? And so it's an application question. It's, are we using the models wisely for the things that they're good for? And Koonin doesn't ask that question at all. He just assumes that if a model has a flaw, it's a bad model. And that's completely backwards. All models have flaws. All models are simplifications of the world.
Right. Thank you so much for it. And we now have questions. So I'm now formally opening it up to everybody who's done it. I hope you have some time to take some questions.
Yeah, absolutely. We can do some questions. That would be good.
Okay, so the first question is from my young colleague, Bhupesh, who works on data and science, and he's worked on weather-related stuff in the past. The question is, he thanks you for a great session. How can artificial intelligence and machine learning improve climate models?
Yeah. Oh, that's a lovely question, and one that I've been thinking a lot about. And I don't talk about it in the book. And yes. I kind of feel now the book is out, I kind of feel I missed a trick there. It's version important. Yeah, maybe version 2. And to be honest, as I said, this book took a long time to write. I actually really finished the main manuscript about 2 years ago. And in those 2 years, there's some finishing work with a book. It takes time to do all the publication process. And I was busy with other things. But in those 2 years, we've made tremendous strides in bringing machine learning in to this modeling process. And I have a whole set of grad students. All my grad students are now focused in on this question: how can we use machine learning techniques to improve the models? So there's several things you can do. One is, there's areas of the models, as I said, where we're less certain. And typically they're things that are hard to simulate in the way I've described. You have these grid points on the planet, and you calculate what's happening with all the variables at each grid point. Well, there are some things on the planet that are too small. So clouds and ice crystals, for example, in clouds happen on such a small scale that you can't simulate globally what's going on. The computational resources would be too big. So you bring in a machine learning modeling algorithm, you show it all the data that we've collected on the small scale about how clouds form, and it learns the patterns, and you take what it's learned and you plug that back into the full model. So we can use machine learning to supplement the places where we know these models are weak by learning from observed data, learning the pattern, and putting that back into the global model. So that's one thing you can do. There's really interesting work going on from both Google and NVIDIA, who are really interested in how you run these models on their GPUs? I'm blanking on the name here. So again, GPUs. Yes, I'm going to remember the acronym. They want to see how you'd run these models on GPUs. And over the past year, they've made great strides in kind of short-term weather forecasting or seasonal weather forecasting, which is a kind of precursor to the climate modeling, where they can take these massive data sets that we have from planet Earth and they just train the machine model, the machine learning model, to simulate what a weather forecasting model would do. And over, even just in the last 8 months, they've got to the point where they can give some of the weather forecasting models a run for their money. They're getting up to the skill of a weather forecasting model. And so there are people now saying, okay, can we extend that to climate models? If you can train a weather forecasting model using machine learning techniques, can you train a climate model? So now you'd never have to build the kind of model I've just described. You just show it all the data that we have over the last 100 years and say, learn what's going on, learn the key patterns that matter. Now, of course, it's a lot more complicated than that. These machine learning algorithms are themselves very complex. But I think for climate modeling as a whole, it is harder because we have less data the further back that you go. And the machine learning algorithms are good when we have massive amounts of data that bracket the question that you're trying to get them to respond. They're less good when you have loads of data on one thing, but you want to predict something kind of outside the training set, something that was never observed in the training set. And that's where the machine learning models fall down. So with weather, it's easy, right? We've got plenty of data, even let's say just from the last week, and you say, can I do a one-day forecast by training it on last week's weather? And the answer is yes, you can. If you wanted to then say, can I do a 50-year prediction for climate change trained on the last 50 years of observations of the planet? The answer might be no, you can't, because the kind of climate change that we expect to see based on the simulation models that we've got is like nothing we've observed in the last 50 years. So it would be hard to say, and then you can't do the usual practice in machine learning is you reserve some of the training data to test. So you train it on some and you test it on a portion that it wasn't trained on. We don't have data from 50 years in the future to do that test on. So with the physics simulations, because the core physics is built right into the models, you can say, yes, we can be fairly sure when you run it in a situation we've never observed, because we know the physics is right, we can be reasonably, can't be 100% confident, but you can be reasonably confident that it's getting the processes right. In a machine learning model, it's really not clear whether we do that. So it's exciting. And I think machine learning is going to revolutionize the world of weather and climate modeling. It's already revolutionizing weather modeling, weather forecasting. It's going to revolutionize climate modeling over the next few years. And there are some areas where we know it's going to bring huge advances, and other areas where it's going to be, wait a minute, is that even a good idea? And are we bringing in some of the problems that we've talked about earlier, that you have a model, maybe then you don't know when you can trust it? So the answer is it's complicated, but there's all sorts of really interesting work to be done.
Right. So we have a whole lot of questions. I'm going to pick from them. So I have a question from my young colleague, Neeti, who works with communication. And her question essentially and inherently is, climatic models are very complicated. So how do you, A, explain their complexity to the lay people, or even, younger academic, in a younger academic setting, so that they can be enthused for working on this?
Yeah, that's a good question. I mean, in a sense, that's kind of what I'm trying to do with the book. And it wasn't easy. As we said, the book took a long time to write, took me a long time to kind of figure out how to tell the story. And in a way that didn't require vast amounts of prior knowledge. I mean, for example, one of the things in the book that I've done is I've avoided putting in any equations. And that's because I know a lot of our students will trip over them, kind of that math phobia. I mean, there are clearly some students that say, yeah, show me the equations. I want them. I'm fine with the math. And there are others that as soon as you get to complex equations are gonna run away saying, I have no idea what this equation is doing. So one of my answers to that question is you kind of have to figure out who your audience are and tailor the message for them. So there are some people that will want the math. There are others that kind of want a conceptual understanding of what's going on without diving into the math. There are some people that want real detail. They're going to keep drilling down. They're going to say, well, tell me how this works. And okay, that's interesting. Now tell me how that other thing works. And there are others who say, I just want to get a sense of what's going on because my work is over here and I want to know how it affects me, but I'm not going to spend ages kind of getting drawn into this other field that's outside what I do. So a large part of it is different messages for different audiences. And like when I was writing the book, one of the things that really helped me figure out my audience is my editor said to me, there are a whole load of people out there who might be interested in what you're saying, but who will never pick up a book like this because they don't pick up kind of books that describe science. That's actually a fairly small audience segment, people who read kind of popular science books for fun. And so I thought, okay, that's really helpful, because now I don't have to worry about how do I keep on board an audience who just don't read this kind of stuff. They're never going to pick up the book in the first place, and therefore I don't have to speak to them. So I've written the book kind of on the assumption that, yeah, you're kind of geeky already and you want to know, and you're willing to read a book to get there. And then they said to me, but how do you reach that other audience, the ones that will never pick up your book? And the answer is, well, you do videos, you do podcasts, you write long form journalism in magazines, for example, and each one you'll find a different voice for, and you'll emphasize different things. Some might be more detail oriented, some might be more kind of high level conceptual, some might be more storytelling, and so on. And so, yeah, I guess what I'm really saying is you need a whole variety of different ways of reaching people, and it depends on who your audience is.
Absolutely. Thank you. I've got a very interesting question from a very interesting science journalist who's covered climate change quite a bit. And the question is in two parts. So first is, I'm quoting from his question, is there any science in your experience that compares in complexity and scale with the climate science? Is it the most difficult sciences of all? This is question number one. So while you answer it, and after that, I'm going to go to the second part.
I don't think it's the most difficult science. I mean, how do you measure the difficulty of a science? I mean, I've learned the climate science. It's taken me, so I started this work, 13, 14 years ago. And maybe it took me about a decade to really understand at kind of the gut level what the science is all about and what it's doing. So that's, that's more than an undergraduate degree. That's maybe several degrees.
That's an entire school term.
Yeah. So does that make this a difficult field? It does to some extent. I think you would have to, in order to make a contribution in this field, you will have had to gone through a graduate program in kind of atmospheric physics or oceanography or one of these other related fields. Is it more complex, let's say, than what we talked earlier about particle physics, for example, or astronomy or genomics? I think that's really hard to say. I think in some sense it's simpler than some of those other fields, because the core physics on which it's based is kind of older and more established. Like, we're not appealing to Einstein's theory of relativity. We're basing the model on Newton's laws of motions. These are taught in high school. Similarly with the chemical reactions, a lot of the core chemistry in the models, it's no more sophisticated than high school chemistry. The way that we bring it together is complex, but the underpinnings are not that sophisticated. So if this was work that required me to understand the theory of relativity, I think I would have had a much harder time really getting to grips with it. So in that sense, I think maybe the answer is yes and no. it's simple in the sense that, yeah, the core ideas, I think, are not hard to explain to people. The complexity comes from putting a large number of those things together and understanding the interaction effects. So that's where the complexity comes in this field, and that's where you start to lose it and say, I really don't understand what's going on here when you marshal feedback loops that involve ocean currents and atmospheric processes and atmospheric chemistry and so on, and the interaction of them all. Then it gets complex, but you can kind of work your way up to that level of complexity.
Right. So the second part of this question is, how do you cope emotionally and socially with what the models are telling us about our future?
Yeah. And this is a really important question as well. So it's hard. I mean, if you take, if you sit down and really think about the future and what the models are telling us, and especially some of the worst case analysis, it's really depressing. It's like, especially when, as I was putting together the book, the realization that the climate scientists have been saying essentially the same thing for more than 40 years and saying, this is what increasing carbon dioxide in the atmosphere will do, and the results will be devastating across the whole planet. And then you start to think, well, what does devastating across the whole planet mean? We talk in euphemisms. We don't talk what that really means. That means death and suffering for millions of people, and in perhaps the worst case, billions of people. It talks about parts of the planet becoming uninhabitable. It talks about food systems collapsing so that people will starve. And, there are moments doing this work where I have got really depressed about it. I've read a lot of what psychologists are now starting to say about dealing with climate change. This whole field of eco-anxiety, this sense of doom that we increasingly have about the future. And there's a whole load of basic tips, like don't work on this stuff late at night. It will stop you sleeping. It will mess you up. Kind of get out in nature and appreciate the world that we have, that we're trying to save. Just taking a walk in a local park or a forest is hugely important for our sense of well-being. So all of that stuff matters, and I do all of that. I have a whole load of practices like that I do deliberately to kind of keep my emotional balance. But to me, the real important thing is there's this lovely book by Joanna Macy, I think is the author, called Active Hope. And what she says is that, hope isn't just something that comes randomly. It's not just something that maybe you can even fool yourself into having hope for the future. She says hope is something you work at. Hope comes from taking action. So the times when I felt most balance and most kind of positive about the work that I'm doing is when I go and work with activist groups, when I go and work with community groups who are pushing forward on some key piece of work, energy retrofits, bringing in renewable energy projects, tree planting, all of the many, many things that we have to do to change the world in order to address climate change. Getting active with those groups is what keeps the hope alive. So for me, that's the crucial thing. It's not just, I don't just study this. I don't just, sit in my lab and then get depressed and then can't sleep because I'm worrying about the future. It's you have to get out and you have to do it with community. You have to do it with other people, and you get out and you do something about it. And that's how you deal with the kind of most depressing side of this.
Right. Thank you. That was insightful, and I think it'll be of benefit to a lot of us. There are still a few questions left, but we are now in the time that we had allocated. And
yeah, and I think that last question was a lovely one to end on, because to me, maybe that's the most important thing from all the work that I've been doing. How do you deal with that gloomy view of the future? And the answer is, yeah, you get active, you join with others and take action.
right. But one of the things, I mean, while I was researching the questions and a whole broad level of stuff, something very interesting, just for you to think about. So I was reading The Guardian, and Guardian is great, right? And you get different parts of the debate. But there was this very interesting feature, and it was at the bottom of the page, while you are reading an article about climate change, how bad it is, why there is no whatever, there's an advertisement from Aramco, right? Saudi Aramco, the biggest oil company in the world, saying how great they are doing for climate change. So perhaps somebody needs to really build resilience like oil companies. They're really there. But Professor, thank you so much for doing it very early in the morning. And for those of us who are going to be watching it later, this is the book. In India, you can get it on everywhere where you get a book. The only sort of problem is that this is slightly pricey for the Indian market. And perhaps with your publisher, the Cambridge University Press, you could have a low, sort of a cheap edition for it for certain markets, because it needs to go out and wide in South Asia.
Yeah, I would love to do that. I fought with the publisher to keep the price as low as possible. I thought I want people to be able to afford it. And yeah, no, I understand. It's still an expensive book for a lot of people.
It's 40 Canadian
cheaper than a college textbook, but more expensive than a novel. Yeah.
It's actually cheaper. So in the Indian perspective, this is $2,500. It's quite expensive. Let's put it like this. An average student or a person who's interested in the field will have to burn quite a big hole in their pocket. So, well, we'll be passing this book around for anybody who cares to read it.
And get people to get the local libraries to buy it. I mean, that's the other way that you get hold of a book, right? So ask your local libraries to buy it.
That would be a great idea, but in India, local libraries are slightly not so local. That's one of the problems.
Oh, so getting to the library is a challenge. Yeah, of course. Yeah. Understood.
But any which way, thank you so much for the time. I hope this was a discussion that you do not regret signing up for. And we'll do all of the editing, etc., and send it over to you.
Yeah, lovely. No, it's been a pleasure. Thank you very much.
Thank you. Please take care. Goodbye.
All right. Thanks.